Welcome back to the second part of this lecture. My name is Herman Jurgen. I'm an astrophysicist at the Research School of Astronomy and Astrophysics, which is part of the Australian National University. Now, we just learned before that there are the life cycle of stars, how it works, and when you look at the Milky Way, as you see here on the right, there are many stars in the Milky Way region, and you are probably asking the questions. I mean, if every star is a sun, if our sun is a star, you would ask the question: are there other planets out there, and maybe possible life forms? This was a very important question that astronomers tried to solve. However, these planets around other stars are very hard to find because they are overpowered in their light by the light from the host star. So it took a long time to detect alien worlds. It actually took until 1995 two Swiss astronomers from the Geneva Observatory, where they could announce finally the discovery of the first planet orbiting around a different star, different from our Sun. That led to this new concept, because using spectrographs led into a new research area for astrophysics to search for these exosolar planets. And in the meantime, over 500 planets have been identified as of July 2011 this year. Let me quickly show you how astronomers can detect this very faint signal from planets around other stars. I show you this here with the help of this little movie here. What we have is we have the Earth here on the left, and this very bright star that has a planet orbiting around it. In this frame here, the star orbits around the planet. It is invisible because of this very bright light from that star. However, what we can do is we can measure the gravitational effect of this planet on the star. And that is shown here with the help of this spectrum. That's a spectrum of the star, and you have some absorption lines. And these absorption lines are moving back and forth. When the planet orbits around the sun orbits around the planet, then you see how the spectral lines changes as a function of time. So over time, we see them moving back and forth. Sometimes the star is coming towards us, and sometimes the star is going away from us. And that is shown in the fingerprint in the spectrum. So that's an indirect way of identifying planets around other stars. Let's come back to the question, how big is the universe? We learned about the geocentric and the heliocentric model just in the first part of this lecture, and let's go now into the 20th century and see how astronomers learned more about the size of the universe. As part of this research, the fundamental question was there: how far are objects like these spiral nebula that I show you here, a couple of photos on the left and here on the right, how far are these objects away from the Milky Way? Now, this is the Milky Way with all the stars, and when you look with the Hubble Space Telescope or with other telescopes into the different regions, you identify these spiral nebula. And the fundamental question was, how far are they away? Are they part of our Milky Way, or are they further away? This whole discussion about the size of the universe led to the famous great debate before the US National Academy of Science on the 26th of April of 1920. And here are the two models that were discussed as part of this great debate. Shapley, the famous astronomer, argued that the Milky Way, there is only one Milky Way out there. It's only one such large object, and this is essentially our universe. So you have the Milky Way, looking here from the side, it's about 300,000 light years across, 30,000 light years thick, and you have all the spiral nebula that I showed you photos before are simply very close objects that belong to our Milky Way. On the other hand, Hippocrates, he championed the idea that the spiral nebula are in fact island universes, like as big as our own Milky Way, but very, very distant, and therefore you cannot see them in details. So this is the model he proposed. You have the Milky Way here with the star that is our Sun, and it's about 50,000 light years across and about 6,000 light years thick. There is nothing between the Milky Way and the island universes, these other spiral nebula, so it is a long, long distance out to the next island universe. Similar to the discussion about the geocentric and the heliocentric model, here in this discussion, both sides had very good arguments, and the case could not be settled. It ended up in a draw. It took another few years to find the answer to which of the two models is correct. It was the famous Edwin Hubble on the 6th of October 1923 who observed with the telescope a very special type of spiral nebula that I show you here on a photographic plate. On that night, he took this photo and he identified Nove stars. That's why he put these N letters here and ticked the position where he identified Nove. But then he also realized suddenly that one of the novae was in fact a variable star, a Cepheid star. And that star belonged to this Andromeda nebula. So in other words, if he can measure the distance to this single star, which is part of this nebula, he could also measure indirectly the distance to the galaxy, to this Andromeda galaxy, Andromeda spiral. And that's what he did. Luckily, Cepheids are a very good distance indicator. You can use the periodic behavior of the light curve as a measurement of their distance. And that's what he did. And he wrote a letter to Shapley saying, I believe the range and median magnitude are near 1.0 and 18.5 respectively. And the conclusion out of these measurements was that the Andromeda Nebula is in fact 700,000 light years away from us. So a much, much larger distance than what was predicted for Spiral Nebula by the model of Shapley. Shapley immediately realized the impact of this measurement, and he wrote Hubble back. He immediately realized the impact of this measurement and of this distant measurements of the Andromeda Nebula, and he wrote back to Hubble, this is the letter that destroyed my universe. So he realized his model was not the correct one, but it was the island universe model that is a better description of our universe. Now let's have a look at some of these beautiful galaxies or spiral nebula as they appear in the sky when you use a telescope like the Hubble Space Telescope. It was realized that there are many, many other Milky Ways out there, billions of light years away from Earth, and they have all this beautiful spiral pattern here, like M51, and here. Sometimes you see them face on. It looks by just looking through these different images, it becomes clear. They're relatively flat in their appearance, round, flat objects, where all the stars are arranged and the gas. Sometimes you see them almost edge on, like this in this case or here. Sometimes they are interacting, like as you can see here. So there are millions of galaxies out there similar to our own Milky Way, and each of them have many, many billions of stars. So you're wondering, how does that work together? I mean, we live here in the Milky Way, which you identify as a beautiful strip in the sky of a bright region with many, many stars in it. And then you have the Spiral Nebula, which look totally different when you see images like this. So how does that geometrically work out? I like to compare this with the giant Ferris wheel analogy. When you're standing in front of if you stand in front of a giant Ferris wheel, you realize most of the light that you see from the Ferris wheel is essentially distributed in a disk with slightly a different angle. Very quite comparable to a galaxy which looks like that. Now what happens when you take the ride and you go actually on the Ferris wheel and see the light then. How is the light distributed in that situation? In fact, because you are now in the disk of the Ferris wheel, all the light is now distributed in a 360-degree circle around you. That's exactly what we see here with the Milky Way. Because with our Sun and the Earth, we are living in a galaxy we call Milky Way. Therefore, we see this as a strip in the sky going 360 degrees around us. If you could step outside of our own Milky Way, it probably would look something like this. Our Milky Way is a spiral nebula, and the location here would roughly indicate where we are living with our Sun, in one of the arms of the spiral galaxy. So the Earth with the Sun and the planets are located slightly off the center of the Milky Way. The entire size of the Milky Way is of the order of 100,000 light years. So if you have a friend, if you live here, if you have a friend and you want to communicate over there, it takes 100,000 years to get the message across. And it takes another 100,000 years to receive the answer. A Milky Way, a galaxy, every single galaxy that I showed you before, essentially consists of huge numbers of stars. In the case of the Milky Way, it will be of the order of 300 billion stars. This is making up a galaxy like our Earth. Now, I show you a little movie here that shows roughly how we imagine today the universe looks like. So we have here indicated with the arrow, that's a simulation, so this is not real, but this is a very close simulation, very close to what the universe is expected to look like. We have a galaxy labeled here as the Milky Way, and we are now flying through the universe, and to show you a couple of features. The universe looks like a little bit like a neural network. It has many empty spaces, but then large numbers of small galaxies we call dwarf galaxies, and then bigger galaxies which are the spiral and the elliptic galaxies. Let's have a look. If you can browse through, here we go. So if you could take a spaceship and fly through space away from our Milky Way, that's how the universe would look like. So you see these filaments, you're coming across beautiful galaxies here, a spiral galaxy here, and then smaller galaxies, and then you have sometimes huge constellations, arrangements, associations of galaxies here, which we call galaxy clusters. So you have thousands of big galaxies right at the same location. This is how we imagine the universe looks like in our models. Now, the question we can ask ourselves, is that it? Can we all go home tonight and satisfied, knowing that we have a good understanding of how the true universe looks like we're living in? You probably guessed it already. The answer is no. There is a dark side to the universe. Since about the 1980s, there is increasing evidence that, observational evidence, that about 80% of all the mass in the universe is made out of dark matter. And this is not dark matter like black holes or neutron stars or planets. It is in fact a very exotic type of hypothetical matter that is invisible and interacts with us, our own world, only gravitationally. Now I show you here a little dark matter simulation of our own Milky Way, how the mass distribution of the dark matter is expected to be around the Milky Way. Let's have a look. So here we have, this is all dark matter, although it's shown here in bright colors. It's actually the dark matter that slowly forms over time. That's a time movie. It shows you how these different dark matter halos accumulate and merge together to form a Milky Way halo. Let's start the movie. So you can see here, initially with the large number of these subhalos that form and merge together to build a bigger halo that forms here right in the center, And over time, which is indicated here with the redshift, we have a system that we think looks very similar to our own Milky Way. And there are two fundamental observations that come out of these supercomputer simulations. Two observations, namely we have the number of objects that we expect, number of subhalos, of dark matter subhalos that we expect around the Milky Way. About 500, if you do head count, between 500 and 1,000 dwarf galaxies, objects that look very small because of this dark matter size are expected around the Milky Way and distributed in a spherical symmetric distribution, as you can see here. Now this high resolution simulation can be now directly compared to what we actually observe around the Milky Way. Let's have a look at what we see there. This is a graph, a figure that shows you the Milky Way satellite census in 2011. So we have the Milky Way here as an edge-on feature, right here the disk of the Milky Way. And you have labeled here in red, the red dots are labeled the dwarf galaxies that are found around the Milky Way. So if all the dark matter that I showed you before, all these dark matter clumps, form enough stars, you should see them as small little dwarf galaxies being distributed around the Milky Way. What is immediately clear from this comparison between the previous slide and this one here is that the numbers are vastly different. Only about 27 dwarf galaxies are known by today. And the distribution doesn't seem to be homogeneous. In fact, they are following essentially this yellow strip here, which is called the disk of satellites, which is an arrangement totally unexpected and not predicted by cosmology models. A fundamental question that we are trying to answer today is, what is the origin of this discrepancy? I mean, there are two possibilities. Is the theory of dark matter incorrect on galaxy scale, or do observers simply overlooked hundreds of these dark matter clumps with their associated dwarf galaxies? These are the two fundamental possibilities to explain the discrepancy between the models and the observations. Now, in order to address this issue and to find a possible answer, we here at Australian National University and the Research School of Astronomy and Astrophysics, we invested $10 million in a new instrument, a new telescope, which is called the Sky-Ramper Telescope, as shown here. The Sky-Ramper Telescope has a huge CCD array, so essentially a huge camera, and this camera covers a very large chunk of sky with one single image. This shows you the footprint of the camera compared to the size of the Moon and compared to the large Magellanic Cloud that you see here in the background. With this camera, the Research School of Astronomy and Astrophysics wants to scan the entire southern sky blindly. So we don't look at individual objects, but we actually scan the entire sky, accumulating of the order of about 150 terabytes of data, of imaging data in different photometric bands. With this imaging data, we'll be able to data mine the information out of these images to look for very elusive, optically elusive objects like these dwarf galaxies predicted by cosmology theory. As part of this effort, I'm running the Milky Way Satellite Survey, which is this initiative to search the entire southern sky, which is shown here with all these dots. These are individual pointings. The Sky-Ramper survey, the Sky-Ramper telescope produces a survey that scans the entire southern sky blindly. It's a 5-year program, and we analyzed these 150 terabytes of digital images to search, among other things, for these predicted dark matter dominated dwarf galaxies. What we want to address as part of this project are 3 main questions. How are the dwarf galaxies and the dark matter distributed around the Milky Way? So we hope to find many of these dwarf galaxies and the associated dark matter. to see how they are distributed in the southern sky. Is the current cosmologic model consistent with the most accurate observations that we have at the moment with the Milky Way? Another very important question. Is this discrepancy resolved, or does it still persist after the major survey? And every single object is very precious. Every single dwarf galaxy that we expect to find, we want to physically and chemically analyze to find their properties, and in order to understand what makes them the faintest galaxies that we know in the universe. Now, if that was all a bit overwhelming, talking about galaxies, the size of the universe, planets, other life forms, and the life cycle of stars, I would like to conclude with a quote. All our life we yearn for answers. Why are we here, and where did we come from? How did it all begin? Are we unique in this or is there other life form in the universe? These are all tough questions, but sitting under a dark sky and looking up has somehow brought us closer to the answer. Thanks for listening.